Hi guys, welcome to homework 2728. I'll be sharing the slides for this homework right now. Um, so right here we have the very first problem. I'm gonna make this bigger for everyone to see. So it says chapter 27 problem 01. In a Young's double slit experiment, the wavelength of light used is 454 nanometers in vacuum, and the separation between the slits is 2.3 times 10 to the negative 6 meters. Determine the angle that locates the dark fringe for m equals 0, the bright fringe for m equals 1, dark fringe for m equals 1, and bright fringe for m equals 2. So here's the formula for bright fringes and dark fringes, where m runs from 0, 1, 2, 3. Okay, so the bright fringe have just m lambda over d, and then the dark fringe have m plus half multiplied by lambda over d. So we're just going to use this for the first problem, which is the dark fringe for m equals 0, bright fringe for m equals 1, dark fringe for m equals 1, and bright fringe for m equals 2. You just apply this formula and you get those answers in degrees. Okay. And then don't forget these nanometers, 10⁻⁹. The other one, you just convert to SI units while you're solving this. And then the next problem says, chapter 27, problem 23, says the highest frequency that the healthy ear can typically hear is 2 times 10 to the 4 hertz. Assume that a sound wave with frequency travels at 346 meters per second and passes through a doorway that has a width of 0.94 meters. Determine the angle that locates the first minimum to either side of the central maximum in the diffraction pattern for the sound. So that's going to be a bright fringe. Then suppose that yellow light of that wavelength passes through a doorway, and that the first dark fringe in diffraction is located at the angle determined above. How wide is that? So we're going to first of all get the theta right here, but we know that lambda is velocity over frequency, so we're going to put that right here for the A part, since we're not giving lambda as the A part. So the velocity is 346 meters per second for sound, and then we have the frequency given, and then from here we get our angle. Then after getting that angle, we use lambda over W to get the width. So W is lambda over sine theta. So we have lambda, we already got theta, we can get sine theta. And that gives us the answer for the B part. Okay. Now, we'll go to the next problem, chapter 27, problem 35. It says, late one night on a highway, a car speeds by you and fades into the distance. Under these conditions, the pupils of your eyes have diameters of about 7.2 millimeters. The taillights of this car are separated by a distance 1.4 millimeters and emit red light with that wavelength. How far away from you is the car when the taillights appear to merge into a single spot of light because of the effects of diffraction? So we'll first of all get our theta minimum, which is 1.22 lambda over d in this case, and then we get that distance where the tail lights are going to merge, and that is S over theta minimum, and the S is what is given in the problem, which is 1.4 meters, the separation between the tail lights of the car. So this is the distance where you're going to observe them to merge due to diffraction. Okay. Then the next problem, focus on concept, question 12. So light passes through a single slit. If the width of the slit is reduced, what happens to the width of the central bright fringe? So the central bright fringe becomes wider because the angle that locates the first dark fringe on either side of the central bright fringe becomes larger. So that is the correct answer. The rest just have little things that are wrong about them. So the correct answer here is B. Okay. The next problem, focus on concept, question 15. Suppose that you're using a microscope to view two closely spaced cells. For a given lens diameter, which color of light would you use to achieve the best possible resolving power? Then that's going to be the blue light. Then an astronaut barely, that's focus on concept, question 17. An astronaut can barely resolve two objects on Earth's surface, 220 kilometers below. The diameter of the astronaut's pupil is that, and the wavelength of the light he's using is that. What is the minimum distance that separates them? The same thing we did before. We find theta minimum, and then theta minimum is S over H. S is 0.005 meters, which is 5 millimeters. and h is 220 kilometers, 220,000 meters. So from here you get theta minimum, S over h, and then you have lambda, you are finding d. So I want you to put this in for yourself and make sure you get the answer 29.524 meters as your d when you substitute this using this value. So the values you have in your own problem might be different. Then we'll have focus on concept question 19. What happens to the diffraction pattern when the number of lines per centimeter of a diffraction grating is increased? When you increase the number of lines per centimeter, the distance between two adjacent principal maxima also increases. So that is what happens. So that's the correct option there from those options. Then the next problem says the diffraction pattern forms when light passes through a single slit. That's chapter 27, problem 25. The wavelength of the light is 523 nanometers. Determine the angle that locates the first dark fringe when the width of the slit is this and that. So theta is sine inverse m lambda over omega. Is that okay? And then we're going to use m equals 1, and then we find this. So similarly, when the slit width is a different width, you use the same formula and you get the answers that you have right here. Okay. So for a single slit, the formula for double slit, they interchange each other. So this becomes for dark fringe. Okay. A hunter who's a bit of a braggart claims that from a distance of 1.9 kilometers, he can selectively shoot either of two squirrels who are sitting 7.1 centimeters apart on the same branch of a tree. What's more, he claims that he can do this without the aid of a telescopic sight on his rifle. Determine the diameter of the pupils of his eyes that would be required for him to be able to resolve the squirrels as separate objects. In this calculation, use wavelength of 498 nanometers in vacuum for the light. State whether his claim State whether his claim is reasonable and provide a reason for your answer. In evaluating his claim, consider that the human eye automatically adjusts the diameter of a pupil over a typical range of 2 to 8 millimeters. The larger values coming into play as the lighting becomes darker. Note also that under their conditions, the eye is most sensitive to wavelength 498 nanometers. So this is a problem to determine. So the first of all is to calculate theta minimum. So this is separation between his squirrels, and that's the hunter right there. So theta minimum is S over L. And then D, the distance here we have here is 1.22 lambda over theta minimum, lambda over S over L, so 1.22 lambda L over S. So we have lambda for 98 nanometers times L, 1.9 times 10 to the power 3 meters over L, over S, 0.07 meters. And then, so S is the distance between the two squirrels, and L is 1.9 times 10 to the power 3 meters, and that is the distance he is from the squirrels. So from there we can now get D at 16 millimeters. So the hunter's claim is not reasonable because 16 millimeters is beyond the normal range for human eye, which is given to be between 2 or 8 millimeters. So the hunter cannot do that, except he has the eye of a different kind of animal, not human eye. Okay, the next problem here says focus on concept question 02. On a highway, there is a flashing light to mark the start of a section of the road where work is being done. Who measures the proper time between two flashes of light? They have options there. The correct option is a worker standing still on the road. And then focus on concept question 03. Assume that the speed of light in a vacuum has the hypothetical value of 80 meters per second. A car is moving at constant speed of 14 meters per second along a straight road. A homeowner sitting on his porch sees the car pass by or pass between two telephone poles in 7.66 seconds. How much time does the driver of the car measures for his trip between the poles? So you see the answer will be less than the time that the homeowner sees. And how do we get that? Using the time dilation formula. And so here we're looking for delta T naught. So it's going to be delta T, which is 7.66. You're using V to be 14 and C, speed of light, hypothetical, to be 80 meters per second. So if you solve this, take the square root of 1 minus this square over that square multiplied by delta T, you're going to get delta T naught to be the value we have there, which is 4.815. So this is how you solve this problem. Okay. The next problem, so I focus on concept question 06 says in a baseball game, the batter hits the ball into center field and takes off for first base. The catcher can only stand and watch. Assume that the batter runs at constant velocity. Who measures the proper time it takes for the runner to reach first base, and who measures the proper length between home plate and first base? So you have options there. The correct answer is the runner measures proper time and the catcher measures proper length. Then the next problem says chapter 28, problem 06. A spaceship travels at a constant speed from Earth to a planet orbiting another star. When the spacecraft arrives, 11 years have elapsed on Earth and 7.2 years have elapsed on board ship. How far away is the planet according to observers on Earth? So here we're going to use first of all, the time dilation formula here. And when we square both sides of the time dilation formula, the square root side under here, the square root sign disappears. So we look for v squared over c squared as subject of formula. And then when we solve for v squared, we get this, so v is c square root of that. So we're going to solve this delta t naught over delta t, 7.2 years delta t naught delta t, 11 years the longer one. And then from here, we're going to get the distance, which is v times delta t. So this is v, multiply this v times delta t. That's what we're putting to the distance here. So you first of all get v from this substitution where you square both sides. After getting v, you multiply it by delta t because speed times time is distance. That's how you get the distance. Okay. Then chapter 28, problem 1, it says, suppose the straight line distance between New York and San Francisco is 4.1 times 10^6, neglecting the curvature of the Earth. A unidentified flying object is flying between these two cities at that speed relative to the Earth. What do the voyagers aboard the UFO measure for this distance? So we're going to use length contraction. L equals L naught square root of 1 minus G and C all squared. So we're going to use 4.1 times 10 to the power 6 is our L naught, and then we get the L to be the length that they measure, which is going to be less than the L naught. Okay. And then the next problem says, chapter 28, problem 10, the distance from Earth to the center of our galaxy is about 32,000 light years. 1 light year is 9.47 times 10 to the 15 meters, as measured by an Earth-based observer. The spaceship is to make this journey at a speed of 0.9990 c. According to a clock on board the ship or the spaceship, how long will it take to make this trip? So we're going to use the proper length and length contraction formula. And then we use L equals V delta T naught. So we put L equals V delta T naught right here. So this is because V delta T naught. So delta T naught divided by V will be L naught over V on the other side. So from here we get delta T naught to be equal to this length given here, because light years is not a time, it's a unit of distance. So substituting here for L naught V, then you can look at the answer you need. So this is converting light years to meters. So you have to do that for L naught before you substitute the rest here to get your answer in years. Okay. And this is converting year to seconds to year right here. That's how you have the answer in years. So this is a conversion you put in. Excuse me. This is another conversion you put in. So chapter 28, problem 27 says, suppose 1 gallon of gasoline produces 1.1 times 10 to the 8 joules of energy, and this energy is sufficient to operate a car for 20 miles. If a 531 milligram drop of gasoline could be converted completely to thermal energy, how many miles could the car go with that energy? So 531 milligrams is going to give you this amount of kilograms by conversion. And then you're going to have the number of miles the car can go is the energy divided by the joules per mile. Is that okay? So you're going to have 20 miles, 1.1 times 10 by 8 joules per 20 miles. So you divide 1.1 times divide by 20 to get the energy per mile. And then we divide energy by that energy per mile. MC squared for the energy of the gasoline, M times C squared, you've already got in M, divided by the energy per mile. It's going to give you the number of mile. Energy cancels energy, you just have miles left that you can get from this energy MC squared using this mass M times the speed of light squared over the energy per mile you know for gasoline, 1 gallon of gasoline. And then chapter 28, problem 30 said a nuclear power reactor generates 3.8 times 10 to the 9 watts of power in 1 year, 365.25 days. What is the change in the mass of the nuclear fuel due to the energy being taken from the reactor? So we use mc squared, energy is power times time. So mass is power times time over c squared. You are given the power, you are given the time divided by square of speed of light. So see, the time is converted to seconds, 365.25 days is when you convert it to seconds, okay? So how do you convert 365.25 days? So you multiply by 24 hours divided by 1 day, multiplied by 3600 seconds for 1 hour. So these times 24 times 3600 is going to give you this number of seconds. Okay. The last problem for the homework said quasars are believed to be the nuclei of galaxies in the early stages of their formation. Suppose a quasar radiates electromagnetic energy at the rate of 2.8 times 10 to the 4 watts. At what rate in kilogram per second is the quasar losing mass as a result of this radiation? So there's a picture of a quasar, which I don't have here. So this is the rate at which the quasar is losing mass per unit time. And mass is energy over c squared, because energy is mc squared. So from here, if we equate rate to be mass over time, energy over c squared over time, so energy over c squared time under. So when we solve this, we can get our rate. So 1 over c squared energy over time, 1 over c squared average power times time is energy over time. So it's just average power over c squared. That's just the rate. So the average power is given, and the square of speed of light, you get the number of kilograms per second that you need here. So it just reduces this formula to average power over c squared. That solves the problem. Thank you guys, and I'll see you guys next time. I'm not feeling too well today. I'm sorry. I wasn't able to go into too much details, but I hope this helps you to solve the problems of the homework. Have a good one.